All right. So we're back again. Last time we talked about looking at chemicals, ionic chemicals, and recognizing whether they dissolve in water, whether they're what we call soluble in water. And then we taught ourselves, we learned how to write the resulting ions that form when we put an ionic compound that's soluble into water. And we introduced another word along with dissolve. We said that ionic compounds do one extra thing. Do you remember that crazy word? What letter did it start with?
D.
It started with a D. It's dissociate. Dissociate. It's different. What it's saying is that the ions separate from each other. Separate from each other. Okay? So, let us look at this chemical equation here, where we have silver nitrate combining with potassium chloride. Both of those say that they're aqueous, and both of them are soluble. Now, we can remind ourselves of whether or not they're soluble by looking at our solubility rules. Do you remember your solubility rules on the back of your periodic table there?
Yeah.
Okay.
Yeah.
Let's see what solubility rule helps us out with the silver nitrate. Which one tells us that silver nitrate is soluble? Which solubility rule?
Number 2. Oh,
very good. Number 2 says that all salts containing nitrates are soluble. And look, no exception. Ha! That's great. Look at number 2. That's a great rule. All of these salts, ammonium ion, or all these ions, ammonium ion, nitrate ion, perchlorate ion, chlorate, acetate ion, all of them, if the salts contain them, are soluble. Very good. So that's how we would be able to know that silver nitrate is soluble. And another way that we can talk about our ionic compounds that are soluble is we can say that they are strong electrolytes. Strong electrolytes. Do you remember the difference between a strong electrolyte and a weak electrolyte? Do you remember what the difference between a strong electrolyte and a weak electrolyte is? So an electrolyte is just another word for a compound that, when placed in water, like sodium chloride, if I put sodium chloride into water, because of the solubility rules, because it dissolves and dissociates, it results in sodium ion and the chloride ion. All right? So another name for these ions in solution are electrolytes. Electrolytes. So I say if I put this sodium chloride into solution, it creates, the result is these electrolytes. And a strong electrolyte essentially is a compound that when you put it into solution will completely dissociate like that. All right. Here's another compound, AgCl. All right. Do you know the name of that compound, AgCl? Do you know what Ag is?
Gold, silver.
Silver. That's right. Gold. Ag
Gold,
is silver. Au is gold. Ag is silver. And Cl, what's that? Chloride ion. Very good. So silver chloride. Excellent. Now, when I put that into water, does it separate into ions? Let's look at our solubility table to see. Do you see any rules associated with silver chloride? Number 3, what's it say?
Oh, number 3. All chlorides, bromides, and iodides, salts containing chlorine, bromide, or iodine, are soluble except when
Very
combined
good.
with Ag, silver,
Mercury.
and
That
lead,
last one's mercury.
and
Very good. So
mercury.
that's how we know that silver chloride is what? Soluble or insoluble? Insoluble. So if I put silver chloride into water, it stays as a solid, right? It will not dissociate. So we call that a non-electrolyte. Non-electrolyte will not create electrolytes when I put it into water. All right? So, some reviewing. And what we said before we left is we want to become familiar with how to write the ionic equation. The ionic equation given a chemical reaction like this. So I'm going to write the ionic equation for this reaction by looking at everything that's soluble. Now, generally, if they provide an equation for you, it's really easy to tell if it's soluble because it says aqueous if it's soluble. So silver nitrate soluble, potassium chloride soluble, and potassium nitrate soluble. But the silver chloride is not soluble. So to write the ionic equation, we just break up everything that's soluble into its ions. Okay? So if I wanted to do that, silver nitrate would break up into what? What would I break it up to if I needed to break it up into its ions? What 2 ions would it have? Ag and NO3.
Ag,
That's right.
NO3.
Now, what's the charge on the silver ion? Very good. +1. What's the charge on the nitrate?
+1. Oh wait.
You're looking on your periodic table? That's good. There it is.
3.
Yeah. So it's what?
Oh, nitrate.
-1. -1.
Negative
Very
charge.
good. So I wrote silver nitrate in its ions. So what else do I have up there? Potassium chloride. How am I going to write it in its ions? Potassium ion, right?
KCl.
Chloride ion, right, like that, right? Excellent. Excellent. How am I going to break up silver chloride? Am I going to break it up?
AgCl.
And I don't. Why don't I break it up?
No. Because
It is an ionic compound,
it's not,
but it's not
ionic
soluble.
compound.
It's not soluble. Right? Okay, so what is the last product? Potassium nitrate, is it soluble? Yes, so I break it up into its ions. The potassium ion and the nitrate ion. All right? And I kind of already knew because I had the potassium ion right here and the nitrate ion over here. So I could have gone and looked if I had forgotten, but I also had just looked, so that was helpful. So this is called the ionic equation. Strong electrolytes are broken into their ions. And this is really what's happening in this chemical reaction, right? Because I have a container, for example. This reaction says I have this container, and in this container I have some AgNO3, but it's dissolved in water. And now I'm adding it to another container. What does this container have in it?
Water.
Well, it has water, but the chemical inside that water is
water.
KCl, right? Can you see that? Silver nitrate being added to KCl. Not just KCl, but it's dissolved in the water, right? And then I mix these two together, put them in the same vessel, and the result is when the silver ions find the chloride ions, the result is a silver chloride solid, which we call a precipitate. A precipitate. And this is a precipitation reaction because I put two chemicals that were soluble in water together, and the silver ion and the chloride ion found each other and formed a solid. Potassium ion and the nitrate ion didn't do anything in this reaction. Can you see that? They stayed the same on the left of the arrow and to the right of the arrow. They stayed the same. In fact, I can write something that's called the Net Ionic Equation that will cross out the spectator ions, the ions on the right and the left that are the same. So if I cross out the ions that didn't do any chemistry, they didn't change, what's left behind is what we call the Net Ionic Equation. Okay, you see that? And here's a video, or here's a drawing that describes this process. Here I have a solution of lead nitrate and a solution of potassium iodide. The lead nitrate is dissolved in water, and you can think of it as lead ions and nitrate ions floating around, being surrounded by water molecules. And here I have potassium iodide in the solution, therefore you can think about it as potassium ions, the blue ones, and the iodide ions floating around in water. But then when I combine these two together, it makes orange juice. Not really, but it's an orange material in the water, and the material is opaque. You can't see through it. You can't see through it like you could see through these two solutions here. And that's because this is now a solid. Here's another video of two other compounds that are soluble. And I'm going to mix one into the other, and the result is that precipitate. See precipitate? That is the mercury iodide, because we combine sodium iodide and mercury nitrate, and the result is our mercury iodide, that orange color. So you can't see through it. It's a powder. If you were to hold this still for a long time, the powder would float to the bottom, and I would have a pile of that orange dust on the bottom. And that's called a precipitate. All right, so right now we are going to follow these rules when we write ionic equations. Identify the strong electrolytes. We can do that either by, if they provide the chemical and say aqueous, then we know it's a strong electrolyte. Or we can use the solubility rules to see if it's soluble. And then we separate those ionic compounds into solutions. And then we can separate the ions, or then we can show the whole ionic equation and find out what we call the spectator ions, the ions who aren't doing any chemistry. Okay, so here's a chemical reaction. This is barium chloride and lead nitrate. And barium chloride mixes with lead nitrate to form lead chloride and barium nitrate. This is that first type of reaction that I mentioned. It's a kind of what we call double replacement reaction. And it follows this pattern. First, I get an ionic compound. Let's say this ionic compound is AB, where A is the cation, the first ion, the metal usually, and B is the anion, the second metal. Like in barium chloride, A would be barium, and B would be the chloride. And then I mix it with another ionic compound. And again, these are aqueous. They're dissolved in water. And I mix it with another ionic compound that is dissolved in water as well, and we'll call that one CD. C is a cation or a metal. In this case, we could think of it as lead. And D is the anion, the other side, which we could think of as the nitrate here. Then, when I combine these two things together, because these are all ions in solution, they're all free and can interact with each other. The products of this reaction are the metal in front here goes with the anion over there. And the metal in front here, C, goes with the anion over there, B. Usually one of these things is still aqueous, but one of them has formed a precipitate, a solid. So this is double replacement reactions or a metathesis reaction. And it follows this form. AB plus CD yields AD plus CB. And you know, it could be AB plus CD yielding CB plus AD. It doesn't matter that order at the end. But A ends up with D and C ends up with B. So let's write the ionic equation for this reaction here. Okay? Can I break chloride up into its ions? Yes. How did you know?
Yes. Because
It's an ionic
one's,
compound and it says aqueous right there. So that's
it's an
another way we
ionic
can know
compound.
it's soluble. So what are the ions that are going to result when I break that up? What's barium going to form?
You're going
Uh-huh. What's the charge on it though? It's element 56.
be aqueous. Oh.
Positive 2. Very good. And then what's the other ion?
Positive 2.
Chloride, Cl, chloride ion. Cl, what's the charge on the chloride ion?
Chloride.
-1. Very good. Is that right? Am I done or am I missing something?
-1.
Aqueous, that's right. Very good. Anything else I'm missing?
Aqueous.
Okay. Do we have the right number of bariums?
Nope.
All right. 2 chlorides. Very good.
We need 2.
And they're going to combine with what other ions?
2 and 4.
Very good. What's the charge on the lead ion? And what's the charge on the nitrate ion?
Nitrate.
Element 82.
That is
Lead? No, lead is element 82. Pd is palladium.
I thought it was 46.
That's 46. Pb is 82.
Oh.
That's a good guess. But in this case, it's not right. Because we can see
-4.
that, what's the charge on a nitrate? Do you remember? What do you mean backwards?
It wants to go backwards.
Oh. Yep, that's right. It wants to lose some, but the nitrate, NO3, what's the charge on the nitrate ion?
It always wants to lose some.
No. Find it on the polyatomic ion. What did you say? -1. Very good. So it's -1. And how many of those -1s did I need
-1.
to balance the lead? 2. So I needed 2 of those. So what does that mean the charge on the lead is? Nope. If I needed 2 of these -1s, it means it was a +2. Does that make sense? Do you follow that? Huh? Okay. Great. Now, what's on the other side of the reaction? What do I write down? What is the name of that?
Lead
Do I have to call it
chloride.
lead something, some number, chloride? It's a solid, very good. But do I have to... Very good, lead 2, because I know that the charge on the lead is a +2, because there's 2 chlorides, and each chloride gives a -1. All right, what are the ions that result from the rest of the material? Very good, barium. What's the charge on the barium ion? Very good.
Barium.
And what's last?
Plus
Very
2.
good. -1 charge.
NO3.
Is that it? Am I done?
Next.
You need to add aqueous.
Oh, good. Yep. Aqueous. Anything else?
Oh wait, you need to add aqueous in front of.
2 in front of the nitrate. Very good. Excellent job. So that is
And
our
put a 2 in
ionic
front of the
equation.
NO3.
Excellent. Do you want to try to do the next one? Do you want to try to write it down for yourself? Okay.
Sure.
So why don't you write down the chemical equation on top? I'll tell you what it is. It's sodium carbonate, Na2CO3,
They're trying to figure it out.
Remember, you need to write down the ions, right? What is Na? What ion does Na form? Yeah, but the ion means it has a charge. What is the charge on the sodium ion?
Oh, it is positive 1.
Yeah, positive. And that 2 doesn't go at the bottom, it goes in front now because we're trying to say that we have 2 sodium ions. Very good. Now, what other ion do we get there? Okay, good. No, CO3 is the polyatomic ion. Right, there you go. CO3 is the carbonate ion, so now we have to look on the periodic table or on the back there to find out what its charge is. Or maybe you can know because of the sodiums, the number of sodiums.
CO3 is on the back. CO. -2.
Very good. -2.
And then now.
Very good. Now we need to break down the calcium chloride, right? Because it's aqueous also. So in the ionic equation, it has to be written as ions. So we have calcium ions.
Calcium. Positive 2.
Positive 2, very good. And chloride ions. Is it minus 2?
Yeah.
How do you know?
I looked on the. Oh no. -1. Oh wait, just minus.
Yeah, minus 1. So how is it that 2 or a plus 2 calcium ion was balanced with 1 chloride ion? 2. Very good. Excellent. Draw an arrow and then draw the rest down below on the next line. Very good.
Now that's solid.
That's aqueous.
So then it's Na plus wait, this one positive charge plus L A 2 A 2 and plus ACO. All done.
Okay, did you write solid on that calcium carbonate at the end? Very good. Now, tell me how many sodium ions I have on the left side of the equation. How many sodium ions are there?
Sodium 1.
Isn't there a 2 in front there?
Oh yeah. 2.
How many sodiums do you have on the right?
2.
But down in your equation down below, I only see 1.
Oh, there's no 3.
Okay, now what about chloride ions? How many chloride ions? Very good, 2 chloride ions. Fabulous job. That was really great job. Excellent work. Okay, let's go back then and look and see what we need to do next, because the next step is get rid of the spectator ions. The spectator ions. How can you tell if something's a spectator ion?
It's not an ion.
It doesn't change from the left side of the equation to the right side of the equation, right? So if I have this equation here, can I find the one down here on the bottom of my screen? Can I find which ions don't perform any chemistry in the process? Or in other words, they're the same on the left side of the equation as the right. See any? The barium ion, very good. This is our spectator ion, so that's not going to be in the net ionic equation. What else? That's right. The 2 nitrates aren't going to be included. So the net ionic equation is just going to be those 2 ions coming together to form that compound. Why don't we go to yours and see what you have to do to make it the net ionic equation?
Any 2, there's
Huh?
2. This one. Whoa. That one's crushed down. Na2. And then Cl. Cl is is the exact same.
Okay, good job. So you crossed out the 2 sodium ions and the 2 chloride ions, and what's left is the carbonate coming together with the calcium to form calcium carbonate. So that is called our net ionic equation. Excellent job. Fabulous job. Okay, so that'll be a good place to stop. Good work today. See you next time.